In this video, we're going to determine the equilibrium constant for a reaction. So in this reaction, we have nitrogen monoxide reacting with hydrogen to form nitrogen gas and water vapor. And here's the information we're given. So we have 0.100 moles of nitrogen monoxide, 0.051 moles of hydrogen, and 0.100 moles of water, and they were placed in a 1 decimeter flask at 300 K, and we have the following equilibrium. And at equilibrium, the concentration of nitrogen monoxide was found to be 0.062 moles per decimeter. So we'll use this data and we're going to make an icebox, and then we'll calculate the equilibrium constant. So here's our icebox. I stands for initial, change, and equilibrium. So that's initial concentration, the change in concentration, and the equilibrium concentration. And at the top here, you have the species that appear in the balanced equation, and don't forget the coefficients as well. The numbers in black are the ones given to us in the question. The numbers in red are the ones that we have to calculate. So from the question, we start with 0.100 moles of nitrogen monoxide, 0.051 moles of hydrogen gas, and 0.100 moles of water vapor. And at equilibrium, we have 0.062 moles per decimeter of nitrogen monoxide, so that's in here. If you're not given a value for the initial number of moles of any reactant or product, you can assume that it's 0, so that's why we have 0 for the nitrogen. So we'll start with the nitrogen monoxide because we are given the equilibrium concentration, which is 0.062. And we have the initial, so we can subtract the equilibrium from the initial, and that will give us negative 0.038, and that's the change in concentration. So once we know one of these values, we can calculate the others. Now you look at the coefficient in front. The coefficient is the same for the nitrogen monoxide and the hydrogen, so the change between the equilibrium and the initial will be the same. So in this case, it's negative 0.038. So if you subtract the change from the initial, you get the equilibrium concentration. And next we'll do the nitrogen. So we start with 0 moles per decimeter. So the only way we can go there is a positive value for the change. And if we look at the coefficient, it's 2 for nitrogen monoxide and it's 1 for nitrogen. So the change will be half as much. So half of 0.038 is 0.019. So our equilibrium is 0 plus 0.019, and that gives us 0.019 moles per decimeter for the equilibrium concentration. So next we'll do our water vapor, and the coefficient is the same for the nitrogen monoxide and the water, so the change is going to be plus 0.038. So we add the change to the initial to give us an equilibrium concentration of 0.138 moles per decimeter. So now that we have our equilibrium concentrations for the reactants and the products, we can move on to the next stage of the calculation. So here we have the equilibrium concentration for the reactants and the products, and next we need to write the equilibrium expression for the reaction. So it's the concentration of the nitrogen multiplied by the concentration of the water raised to the power of the coefficient, which in this case is 2. And that's divided by the concentration of the NO, again raised to the power of the coefficient, which is 2, multiplied by the equilibrium concentration of the hydrogen raised to the power of the coefficient, which again is 2. So the next step is to input the equilibrium concentrations for the reactants and the products. And when you do the math, you end up with a value for the equilibrium constant, which is 5.6 times 10 to the 2 at a specific temperature. And our final answer is given to 2 significant figures because that's the least number of significant figures in our calculation.